to our seminar. We are very pleased to welcome today's seminar presenter, Tristan Brown. Dr. Brown is Associate Professor of Energy Resource Economics in the Department of Sustainable Resources Management in the State University of New York College of Environmental Science and Forestry. And he also serves as Director of the Bioeconomy Development Institute at that institution. His research interests include carbon, economic, and ecological effects of bioenergy and bioproducts. Dr. Brown, welcome. We look forward to your presentation in today's seminar.
Thank you very much. Pleasure to be here. Let me pull up my screen. Okay, so I'm going to be talking about techno-economic analysis, and just want to note this is a very high-level overview of techno-economic analysis. If you wanted to learn how to do, proper TEA, which is the acronym that we use for this, you could probably take a course that would last an entire semester. It's a very, very deep field at the end of the day. There's a lot going on with it, so I'm not going to teach you how to do it, but rather give you an overview and introduce you to some of the more important concepts when it comes to doing TEA. So let's see if this will let me. There we go. So always like to start with a definition, what techno-economic analysis is. The name gives you a little indication, right? There's clearly a technical side to it. There's certainly a lot of economics going on with it. And what techno-economic analysis really is a cost estimation methodology. Right. This is something there's a lot of confusion about. A lot of people, wonder what this is. It really fundamentally is just a cost estimation methodology. And what we use it for is to calculate project costs within approximately plus or minus 30% of what we would expect actual costs to be. So, that definition right there gives you a pretty good idea as to what we're talking about, right? This is not going to be an incredibly rigorous, multi-year analysis that you're going to do, right? Frequently we'll see these types of project estimations done, and they're very, very, very detailed, right? They can literally take a team of people 1 or 2, even more years to conduct. This is much higher level than that. This is kind of an initial estimate. I'm not going to call it a back of the envelope estimate, right? But this is going to be something that you're going to do as kind of a starting point to determine where you can delve in further. Where it says plus or minus 30% of actual costs, right? That kind of gives you a range of uncertainty that you can expect with this. And, especially when we think about, bioenergy or bioproducts, when you start thinking about production facilities, these are facilities that are going to cost in the hundreds of millions of dollars, possibly more. And so, it's the type of thing where if you're going to secure funding, you're going to have to do a whole lot more than an initial TEA to secure that funding. But what TEA allows you to do is to start narrowing down processes and procedures. And as we'll talk about later, I'm really glad that we're going to be hearing about LCA in a couple of weeks, because this also pairs very nicely with life cycle assessment to help understand some of the environmental impacts in addition to the economic impacts. So TEA is very similar to your standard financial analysis tools. If any of you have a financial background, especially securities analysis, that type of thing, net present value, internal rate of return, payback period, right? These are all very, very basic concepts you'd be familiar with. TEA is very similar to these financial analysis tools because they are frequently employing them. Most TEAs are going to use net present value analysis or are going to use internal rate of return calculations. So there's a lot of overlap between the two, but that doesn't mean that it's a perfect overlap. And so they're very different in terms of the types of projects that the methodology is going to be applied to. So where, a standard financial analysis is going to be utilizing market prices, things like that. With techno-economic analysis, we're going to be understanding pathways that have not yet been commercialized, that are not widespread, where you can't just, open up a catalog, an equipment catalog, and say, okay, this is what this particular piece of equipment costs if I want to build this facility. It's more complex than that. So the reason we use techno-economic analysis, though, is because we ultimately want to understand if we deploy a pathway, what's the likelihood that it's going to be financially competitive with what we're currently competing with, right? And so, when it comes to the bioeconomy in general, this is very, very important because, as we all know, most bioeconomy pathways, whether it's biofuels or bio-based products, the reason they're not commercialized is because they are not cost competitive with the existing fossil fuels, right? And this has been true for over a century for many of these different products and fuels. So we have to understand what's going to be necessary for them to be competitive so that we can then start looking at, well, how can we make improvements? What types of policies do we need in order for these to be truly competitive with fossil fuels? And this is becoming especially important as a growing number of governments around the world start to move towards displacing fossil fuels, right? We recognize there's all these negative externalities associated with them. And so we're trying to move away from fossil fuels. And so we have to figure out how to incentivize the alternatives. So just to give you an example, right, where we start talking about this type of thing, let's say that you are tasked with assessing the project costs for a potential solar PV farm in upstate New York, right? And so by project cost, what I really mean is how much is it going to cost to get this in the ground? What's it going to cost to operate? At the end of the day, you want to know how competitive it's going to be. Well, you'd probably follow something very similar to these the steps listed here, right? You're going to want to know what the solar energy availability and the location is. I'm from upstate New York, where we joke that, basically winter we get no solar availability, and it doesn't matter because the solar panels will be covered by snow the entire time, right? So you need to understand what your solar resource is. You'd need to know what your solar PV unit costs are, right? Because you're going to have to buy these panels and get them installed. Therefore, you're also going to need to know what the installation costs are. You'll need to know the electric rates in the region. Even in a state like New York, right, it can go from 6 cents per kilowatt upstate to 24 cents per kilowatt hour downstate. So that's going to make a big impact. So you have a number of different steps that are going to take place here. What's important about these, this is not going to involve a techno-economic analysis. This is your basic financial analysis. And the reason I say that is because everything listed here is very easy to find via market sources, right? This is not going to require really in-depth analysis to understand these things, right? So let's take the most important factor here, the solar PV unit cost. Solar PV unit cost is as simple as calling up a solar installer and asking them how much their panels cost per kilowatt, right? I mean, these are very widespread. This is a very highly commercialized technology. And so you don't need to do really in-depth analyses to understand what that's going to cost, right? Installation costs, same sort of thing. You call up an installer, you ask them what their rate is. It's that simple, right? Because they're doing these jobs constantly. And so they have a very good market rate there. So for something like this, techno-economic analysis is not necessary because we already know what these are going to be. So begs the question then, all right, when do we use techno-economic analysis? Well, we use techno-economic analysis when the project costs are not going to be available, right? And they are not always available, especially for certain types of technologies. So give you some examples of when they're not available. Let's say the pathway is the result of a very recent invention. So this could be a new wind turbine design. If we think about the bioeconomy, this could be a new type of biodiesel feedstock. So let me talk a little bit more about this. New biodiesel feedstock. The most widespread biodiesel feedstock in the US is soybeans, right? And we've been growing soybeans for decades. We know exactly what the input costs are going to be. You can, literally with a few keystrokes on Google, you can find out what the price of soybean oil is because it's such a widespread commodity. Well, for a long time now, we've been talking about a different type of biodiesel feedstock because we don't have enough soybean oil to go around, which is microalgae oil. And this is not something you can easily find, right? Because we are not currently producing microalgae at commercial scale volumes. So you can't just look up the cost of microalgae oil. If you want to understand what it costs as a feedstock, you're going to have to do a techno-economic assessment of microalgae production. And then you need to look at conversion, things like that. So if you're talking a recent invention where it has not achieved market penetration yet, this is where TEA can come in very handy. Where the pathway requires very large centralized facilities, right? So we think about your standard concentrated solar power facility. It costs about $2 billion for one of these. Smaller, but still something that we're certainly familiar with, right? You look at a cellulosic ethanol plant. When these were being built a decade ago, they generally cost about $500 million. So investors will not want to finance such of a facility until they know if it will work or not. And so again, this is where techno-economic analysis comes in. Something like cellulosic ethanol, right? I say when these were being built a decade ago, we don't have them anymore. They shut down, right? So if you want to understand whether or not a cellulosic ethanol facility will work, you can't look at an existing facility because there are no existing commercial scale facilities in the US anymore. And so again, this is where techno-economic analysis comes into play, is to start looking, okay, what would this cost based on what we would consider to be a feasible arrangement? And then especially when we think about bioeconomy, where it becomes very relevant, pioneer first of kind plants that have been built at smaller scales, but not at commercial scales. Scale is a critical component in techno-economic analysis, as I'll talk about in a few minutes. And so what this really means is when we think about new fuels or new bio-based products that have not been deployed yet, where we've succeeded in building them in the lab, maybe we've even succeeded building them, at a pilot scale, but we have not moved up to that first pioneer commercial scale facility. Techno-economic analysis is a very valuable tool in those situations because we don't know what the project costs are for that first commercial scale facility. And yet we really need to understand what those would be. And then really complex technologies, right? So we think about, sunlight to jet fuel via microalgae hydroprocessing. We aren't doing this even at, pilot scale all that much yet. So, very complex. There's a lot of process steps involved, multiple conversion steps that are going to be required. And so we have to be able to understand what the costs are at each one of those steps, right? Even like I was talking about, if you convert microalgae biodiesel, you need to know how much the microalgae costs to produce, then you need to know how much it costs to convert that to biodiesel, right? Multiple steps that you need to understand. So why TEA? Well, we use TEA to fill those gaps, all those different areas where we don't know the project costs. We use it frequently to conduct scoping analyses where multiple next generation energy pathways are being compared, right? Especially at the level of policy making. Policymakers understand what we need to get to, but they don't necessarily understand how we get there. And so a scoping analysis using techno-economic analysis is a great first step to understand, well, this is approximately what it would cost to achieve a certain level of output of a product that we do not currently produce. Location. Location is another critical component of any bioeconomy system, and especially the techno-economic analyses we do, because the location is going to determine what your costs ultimately are. It plays a very big role. And so TEA is also useful for conducting a location analysis where one or more next generation energy pathways are assessed across different locations. So this can be as basic as trying to determine what an optimal location is. This could be something where you're trying to determine, which pathways are going to make sense in which locations, right? Again, you haven't deployed these. There isn't much market penetration going on yet. So you need to do those initial assessment steps. And then broadly assess the economic feasibility of a next generation energy pathway. And where this becomes very critical is when you start looking at different policy scenarios. We have a lot of different policies in the US in support of the bioeconomy, but they're all very different, right? Yeah, the federal renewable fuel standard, which is very different from California and really now the rest of the West Coast low carbon fuel standard, which are very different from the various tax credits that are available at the federal and state levels. And so understanding how these policy scenarios are going to work and how they're going to function and what they're going to incentivize and won't incentivize when you're talking about pathways that have not yet been deployed, you need something like a techno-economic analysis that can start giving you some guidance regarding that. Okay, so TEA does have a lot of limitations though, and there's certainly going to be a number of scenarios where you do not use TEA. This is not going to serve as a replacement for a site-specific cost estimation analysis, right? So if you've decided, okay, you're going to build this $500 million cellulosic ethanol facility, you know where you're going to build it, you have everything figured out, you need to know how much it's going to cost to build so that you can start securing the financing. This is going to be very different from that, right? Because that is going to be very nuts and bolts understanding for the very specific location, very specific considerations, factors, et cetera, what that's going to be. TEA is higher level than that. TEA is not going to go into that level of detail. Can serve as the basis for that level of detail, but it's not the same thing. TEA cannot be used to conduct environmental impact assessments. They can be linked. We'll talk about LCA in a little bit, how they're linked to LCA, but TEA is strictly the engineering economics of a system. It is not going to tell you anything about the environmental economics or the ecological economics of a system. You can generate highly detailed pathway cost estimates, right? But you're not going to have that level of granularity that's necessary when you're trying to get, very specific. So that said, the other thing that TEA is not is a process model. So a lot of you are familiar, especially if you ever taken engineering courses, you're very familiar with process modeling, right? Things like Aspen Plus, SimiPro, et cetera, right? And a process model in that context is ultimately where you are determining the actual mass and energy flows of a system. Now, process models are often used to build techno-economic analyses, but a TEA is not a process model. All right, so that's another important distinction. This lecture, when we talk about TEA, I'm going to be assuming that if you're building a TEA, you either already have a process model or you're adapting an existing TEA that in turn was built on an existing process model. So TEA, very closely linked to process modeling. Frequently a process model will be the first step to building a TEA, but TEA is not the same thing as an engineering process model. Okay, so when we look at a TEA, there's a couple of major variables that we really are the most important variables of everything that we have. And that's really what comes down to the production cost, or you could also call it the manufacturing cost. And to understand that, right, so when we talk about a production cost, what we really mean is, let's say that you're talking about cellulosic ethanol, because we've been using that example. The production cost is literally the cost to produce a gallon of cellulosic ethanol at a particular type of facility, right? And so it's a very straightforward number. It's easy to understand. It's easy to then compare with the market price, figure out, is this going to be competitive or not? But calculating a production cost is more difficult. And there's going to be two important quantities, two variables that we really have to know in order to do that. The first is the capital cost, and the second is the operating cost. And these are two different things. Capital cost is simply the cost to build a facility or plant, right? So you want to produce cellulosic ethanol, you're going to have to build a cellulosic ethanol production facility. The capital cost is telling you exactly what that's going to cost to do. But that's a one-time thing, right? You build that facility, you're typically going to run it 20 to 30 years. So capital costs are one time. They're usually only incurred at the very beginning of the project, maybe some repairs and maintenance, but nothing beyond that. The operating cost, on the other hand, is what it actually costs you to operate that facility for the 20 to 30 year life. And so this covers a lot of different variables. It's, no pun intended, it's highly variable, right? These are going to change over time. Generally, operating costs are a function of your production throughput. So, the more input you have, the more outputs you have, going to affect your operating costs. And these are going to be over the lifetime of the project. So production costs ultimately are going to be a function of both, because the capital cost does have to be paid off over time, right? You have to, take out a large loan, you're going to have to pay that loan back. So capital costs are paid back over time, and that's going to be reflected in your production costs. And then your operating costs, right? To think of it this way, we can think of a refinery, just your modern petroleum refinery. Operating costs, we know that plays a very big role because everyone's seen what's happened to fuel prices recently, right? Gasoline prices have skyrocketed. Well, gasoline prices have skyrocketed because the input to refineries, which is crude oil, has also gone up steeply. And so that's right. You can just think about how the price goes up and down, and that's going to affect the operating costs for that facility. A lot of other variables as well. We'll talk about what those are, but it's important to distinguish between the two because capital costs, they're one time up front. Operating costs are over the lifetime of the project. Okay. Before we talk about capital costs, I'll also just make a note because this is something I'm constantly having to discuss with my graduate students, right? This is one of the first things that they learn is that there are good ways and bad ways to present capital cost data. The capital costs are typically quite large, right? We're talking tens, hundreds of millions, even thousands of millions, or ultimately billions of dollars. And so how you present those numbers are going to be very important. And so just take, an example here. After making assumptions about capital costs, labor costs, fuel costs, enzyme costs, so on, two consulting companies, they're conducting a techno-economic analysis, report a grassroots capital cost for a 110 million gallon per year cellulosic ethanol plant as follows, right? Two different numbers. One is 11 digits long. The second one is only 3 digits long, right? 527, et cetera, et cetera, et cetera, or 530 million. For techno-economic analysis, this is important to understand, right? We're generally going to want to do the second one rather than the first one. Now, if you're talking a very site-specific analyses, that's where that first one comes in important because you need to know every single penny. But the reason I say that, for the techno-economic analysis, fewer significant digits is important. Again, we're talking about a plus or minus 30% range of uncertainty. So when you calculate out to the individual dollar or worse, the individual penny, doesn't really work because you're already talking a plus or minus 30% range of uncertainty. So when it comes to which number can you more readily recall, it's company number two's estimate, right? This is much easier to remember. Which number better reflects the uncertainties in the estimate? And this is why this is important from an analytical rigor standpoint. Company one's estimate suggests that they have accurately calculated this to the individual penny. For techno-economic analysis, plus or minus 30%, that's not true. And so fewer significant digits tells you, right, there's more uncertainty involved. And ultimately, you're more likely to trust the one that does a better job of capturing that uncertainty. So this is, when it comes to presenting costs, this is an important component. Okay. So capital costs. We ultimately break capital costs down into 4 major categories. And this is because, everything falls into capital costs here, but there's different types of capital costs that we account for. You have direct project expenses. You have indirect project expenses. You have what's termed contingency and fee, and you have auxiliary facilities. And so most techno-economic analyses, if you're reading the study, you're going to see them broken down into these 4 different categories. And so it's important to at least have a basic understanding of what these are. So direct project expenses, this is that first category. This is essentially what it costs to buy the equipment, and then to buy any materials needed to install the equipment, pay for the labor to install the equipment, right? So this is, the equipment itself. And so you can look at this as, right, you ultimately buy something, off of Amazon that requires self-assembly, right? You're buying the equipment, that's, whatever's coming in the box, you're buying the materials that, the screwdriver or whatever type of equipment you need. Those would be your direct project expenses, right? So pretty simple, pretty easy to understand, right? It's your equipment. This is also categorized as purchased equipment costs and installed equipment costs. And so the easy way to look at this is the installed equipment cost is simply a function of your purchased equipment cost times an installation factor. And we'll talk a little more about installation factors because these are an important component as well. And there's a lot of different thinking about how to handle those, but that's ultimately what we're talking about, right? Buy the equipment, what it's going to cost to get it installed. Category 2 is the indirect project expenses. And it's important to consider these because, especially at a rudimentary level, most people just assume and just calculate the direct project expenses, right? But when you start thinking about these very large projects, and direct expensive projects or direct project expenses are the largest category typically, but there's other categories that do influence your assessment. And so the indirect project expenses, this is things like paying for construction overhead. We don't normally think about this, right? You're building your own desk, you don't care about most of this, but when you have a large project, you're paying people to build this, and you're not just paying them in cash, right, via their salary. You're going to have benefits, right? Typically, labor is going to have health insurance, sick leave, et cetera, maternity leave, things like that. So depending on the state you're in, you could have very large benefits, you could have smaller benefits, but there's going to be benefits associated with your employees, the labor that's building this. You're going to have salary and benefits for the labor supervisors because you're probably not going to be doing the supervision. You're going to have things like machinery rentals, small tool purchases, right? Different from, say that screwdriver we're talking about, but you're going to have equipment that's associated with this indirectly. And so these are another category of costs that we typically account for. Engineering expenses. A lot of engineering expenses that are going to go into these big projects. I give the classic example of this, right? So I can't remember which company. It was one of the big oil giants. Actually, I think it was Royal Dutch Shell. Back about 20 years ago, they were going to build a large gas to liquids facility in the Middle East. I think it was Qatar. And it was going to take stranded natural gas and convert it to liquids because this was about the time, right? We thought we're running out of petroleum. We're talking very high prices of petroleum, et cetera. And they did a great assessment, or what they thought was a great assessment. And they said, okay, this facility to build it's going to cost about $6 billion. The problem was they hadn't taken into account the land on which this facility was going to be built. It turned out that there were a lot of structural issues with that land. And so there ended up being far more engineering expenses than they had originally assumed. When I say far more, this facility ended up costing them $24 billion, right? So we're talking about several, multiples greater than what they had estimated. So this is why we account for things like engineering expenses, because that type of thing it can be a very large thing, not that large typically, but it's important. So indirect expenses for TEA purposes, though, they're commonly calculated as a function of direct expenses. And so, again, not always going to be the case. This is why we have plus or minus 30%. But at least for our type of high level assessment, if you know your direct expenses, we typically calculate indirect as a function of that. There's contingency and fee, right? Classic example, like I was just talking about, contingency is going to be unexpected costs. This can be considered your factor of safety. Assessments that have been done of cost estimation in general, right, whether it's TEA or more site-specific projects, find that analysts tend to exhibit bias. We tend to underestimate how much a facility is actually going to cost. And so contingency is important to include in there, right, because we do tend to underestimate these things. And so you want to include that margin of safety, that factor of safety there. And then the fee is the profit to a company performing the project, right? Whoever's building it, paying for all that labor, that's just part of it. There's also going to be a fee on top of that. And then finally, as auxiliary facilities, you're not always going to see this in the TEA because it's just appropriate to some projects. This is going to be things like administrative offices, laboratory, maintenance shop, warehouses, right? Cellulosic ethanol facility, they're going to have a laboratory because they have strains, microbial strains that they have to take care of. Other types of bioeconomy projects, though, not necessarily going to have that. So it is very, very pathway specific. All right, so when it comes to calculating the capital cost, there's three main methodologies that we see. And so just briefly go over these because they are different. And this is going to have a pretty big impact on what your result is, but you will see all three of them if you study the literature enough. You have Lang factors, you have what's termed module, also known as hand factors, and then you have the Peters and Timmerhouse factors. And each one's used different ways, but they have their pros and cons to each one. Lang factors are generalized factors representing installation and labor costs according to a broad facility category. And so we've kind of moved past these, but you'll still see them in some of the older literature, so it's worth mentioning. This is a very, very simple methodology. You basically just take your purchased equipment costs, you determine, is it a solids processing, a fluid processing, or a solid and fluid processing facility. You figure out what that Lang factor is based on this table here, and you multiply it by your purchase equipment costs, and that will give you your total capital costs. So very basic. These numbers have shifted a bit, as you can see, over the last few decades. Anytime you have it this basic, right, tells you that you're probably going to have more uncertainty. And so we don't use these as much, but it does give you an idea as to how things used to be done. And the idea here was solids processing was going to be less expensive than fluid processing, because fluids, you basically had to make sure there's no leaks. Sometimes it had to be under pressure. And so it's just reflected in what those Lang factors were going to show. More complex is what's termed the module factors or hand factors, and these employ different installation and labor factors according to broad equipment category. So, more difficult to do, more time intensive, because you have to actually break down your different equipment types rather than saying, well, we're just handling solids or we're just handling liquids. Module factors employ different factors according to that narrow equipment category. So, if you have pressure vessels, that's one factor. If you have fired heaters, that's a different factor. And so you go through, right, every different type of equipment you have, and then you calculate out, basically what that total project investment for that particular type of equipment is, and then you sum it all together, you get the full total project investment for the site. So more complex, more time intensive, but ultimately we tend to move more in this direction as a result. Now, when I say more time intensive, right, you just give you an idea, there's a lot of these. So, we're not just talking three like you see with the Lang factors. There's ultimately quite a few of these. And so this is where, you are going to require more time. And so, this is the type of thing we'll see more frequently in, say, a PhD dissertation, right? Because, you're going to be more comprehensive with what you're analyzing. The most recent development, and this is the one that we see most common nowadays, is what's termed Peters and Timmerhouse factors. And these are done rather differently. Unlike the Lang, the hand, the module factors, Peters and Timmerhouse factors employ factors representing each aspect of equipment installation. So we're not talking about equipment types, right? This is more general than equipment types, but it's more detailed in terms of the types of processes that are going to be utilized. So the Peters and Timmerhouse factors also employ methodologies for calculating indirect cost, contingency, working capital, and even land. So more comprehensive in terms of what's going into your assessment in that regard. This is a classic example of Peters and Timmerhouse factors. Some differences, right? So this is what the national labs have been using for over a decade now. And sometimes you'll see, right, the individual percentages here are going to be different, but ultimately all of the costs here are just a function of your total purchased equipment costs that we were talking about earlier. And so, it's a percentage of that, and you sum all those up and you get, right, you've got some that are for installation. You see indirect costs down there, and you've got the direct costs, indirect costs, right? And then you start working your way through. And so the advantage to the Peters and Timmermans factors is, you go through, you calculate out what your purchased equipment cost is, and you can calculate everything else as a function of that. And this is based on, right, these were many, many years of studies looking at actual projects in the ground that found that in general, right, for each particular step, whether it's the piping or electrical systems, in general, it's a percentage of that total purchased equipment cost. And so this is what the national labs have been doing for a long time now. We're seeing increasing number of academic analyses that utilize this. So, this is what's probably most common nowadays. When it comes to direct cost, right, this common question I get from students is, how can we calculate this? Especially when we're talking about a newer technology, right, where you can't just call someone up and ask them, what's the cost of building this type of facility? Well, equipment costs can often be determined by obtaining informal quotes from a supplier. And especially for master's and PhD students, this is very, very common, is just call up the supplier and find out. Equipment cost estimation for new technologies or really complex projects can be estimated using tabulations found in the literature. So, especially where this isn't something that's necessarily being sold at a widespread level, greater uncertainty, but this is something that, you also find there's a number of analyses where they are going to be presenting all of this in fairly good detail. All right, so gets you your unit costs, right? You ultimately know what that facility is going to cost for a certain capacity. And this is why I said earlier that capacity is so important, though. Every different project is going to have a different capacity. Capacity is ultimately a function of your feedstock availability, your land availability, your market dynamics, right? There's a lot of different factors that go into just how large or how small that facility is going to be. Now, you might say, well, who cares? Right? As long as you know your unit costs, it's going to cost me this much per gallon of capital costs, right? As long as you know that, we know what we need to know. But that's not going to be the case, right? Ultimately, capital costs are a function of unit costs, but your unit costs are also a function of scale. So we talk about, right, it's going to cost you $500 million to build a 110 million gallon per year cellulosic ethanol facility. I'd say, well, I know what the unit costs are. But that's a function of it being a 110 million gallon per year facility. Higher capacity, lower capacity can change that result. And so in general, as a general rule, the larger capacities result in higher capital costs, but lower unit costs. So let me spend a little more time on that, because this is where we get into economies of scale. And this is one of the most important considerations. The principle of economies of scale predicts that capital costs escalate proportionally slower than the size of a facility. Now, this is not true for all different facility types. We see thermochemical processing facilities have superior economies of scale to, say, anaerobic digesters, right? So there's different, and you can actually get into the literature and you'll find that there's different scaling factors for, different types of facilities. But in general, capital costs escalate proportionally slower than the size of a facility. So there's actually a scaling law, and there's a nice little formula that you can use. Ultimately, what we need to know, if we want to predict the cost of a specific facility or specified equipment, we need to know the cost of that baseline equipment. We need to know the size of the facility we want to build, and we need to know the size of the baseline equipment that we have the cost estimate for. And then finally, we need to know N. And N, and like I said, this is where the literature, it's different for different types of facilities, but N is simply the economy of scale sizing exponent. And so most commonly we will see, and this is the default assumption, is 0.6, right? So if this economy of scale sizing exponent is less than 1, then that tells you as the larger you go, the lower your unit costs are ultimately going to be. And so, we typically see 0.6. There's some situations where you can actually have diseconomies of scale. And so in that case, that will be greater than 1, and then your incentive is built smaller. But in general, we will see less than 1. And the smaller that number is, the closer to 0 that is, the better your economies of scale are. So scaling factor below 1 means that unit costs fall as capacity rises. Greater than 1 is just the opposite of that. And so what that really means then is, for most energy and chemical processes, we really want to know approximately what that scaling factor is. And so this is why I said 0.6 is the standard estimate. It's even known as the 6/10 rule, because it's so widespread. And so frequently, for especially techno-economic analyses, this will be very common. You'll see a scaling factor of 0.6 employed. Again, this varies by pathway. Thermochemical pathways are closer to 0.6. Biochemical pathways range from 0.7 to 0.8. Some estimates show that even something like so an anaerobic digester, you can ultimately get up to 1.2. The other thing I would note, we typically assume that these are going to be linear relationships, but that's not always true, right? So there's going to be, in some cases, you'll have almost an S curve, right? Where, there's going to be economies of scale up to a certain point, and then diseconomies of scale after that point. Where this is especially true is for any type of bioeconomy facility that utilizes a widely distributed feedstock, right? And so the way to look at this is a small facility is only going to need to gather feedstock from a relatively small area. And so it's relatively inexpensive to do so, right? Because you're not transporting that feedstock as far. And so up to a certain point, as that facility gets larger, it's going to benefit from economies of scale with regard to the capital costs. But this is why we treat capital costs and operating costs differently. Operating costs include feedstock costs up to a certain point, right? That's going to be true. And then you go beyond a certain distance and moving that feedstock, and you're suddenly going to start experiencing diseconomies of scale because that feedstock gets more and more expensive to collect as that facility gets larger, right? Because the radius that you're collecting that from gets larger and larger. So, these are going to be variable numbers depending on how detailed you're getting. That's something to consider. But in general, right, we just assume a single factor. We also have to account for inflation factors. And this is especially true when we start talking about types of projects that are based on technology that has been around for, say, 10, 20 years. It just hasn't been deployed yet. And that's because, right, everyone knows what inflation is nowadays because we're experiencing high inflation for the first time in, close to 40 years. But there's always a little bit of inflation. And so, even if when we were at 2 to 3% inflation every single year, that would add up over time, right? 10 years, 20 years, that would start to result in very different numbers. And so if you're using an analysis, right, a cost estimate that's several years old, it's always a good idea to consider the impact of inflation on that. So inflation can increase the cost of equipment over time, and it can be accounted for in estimating current equipment costs. Again, just like scaling factor, we have a formula that can use. All you really need to know is the specified year, right? So your previous year you're taking your estimate from, the year you want to inflate the cost to, and then what that inflation index factor ultimately is compared to the cost of the equipment. That said, this is not as simple as just using the inflation that we read about in the news, right? And so I say, beware of technological change. Well, what I mean by that is monetary inflation tends to constantly increase, right? And so this is what's known as the Consumer Price Index. It's published by the federal government, right? And so you can actually find inflation indexes going back decades, which is fine for monetary inflation, but technological change is not going to apply. And so I'll take the classic example now of solar PV. Right. In theory, under inflation, you would think that the cost of a solar panel is going to constantly get more expensive, right? Because the purchasing power of your dollar gets less powerful every single year. But technological change has driven down the cost of producing a solar PV panel. And as a result, the cost of solar PV has fallen by about 90% just over the last 10 plus years. So technological change is going to be different than what we're talking about here. Even in chemical engineering field, right, which is where a lot of bioeconomy systems are going to play in, we see differences, right, depending on the cost of equipment. And so this is, something where you can actually go back. There's something called the Chemical Engineering Plant Cost Index. This is a really good way to actually calculate out the capital costs over years, right, if you're taking a historical estimate. Because, right, what this is ultimately showing, and you can break this down by individual pieces of equipment, just like we're talking about with, say, the module factors. There's going to be some years where the equipment gets more expensive. There's going to be other years where the equipment is less expensive. And so, you don't want to necessarily assume if you have good information that it's just constantly increasing based on the underlying rate of monetary inflation. The other important factor is location, right? And so especially when we start talking about, a specific area, so not that site-specific estimate I was talking about earlier, but let's say that you want to build something in, Pennsylvania or New York. Chemical engineering capital costs are generally found on what's termed a U.S. Gulf Coast basis. And that is simply because historically chemical engineering has primarily been about refineries and petrochemical facilities. And most of those are in the US, at least, are clustered in the US Gulf Coast. And so the cost estimates and the inflation factors are generally based on the Gulf Coast. And so process models where they put together basically figure out all the equipment, that equipment is assumed to be coming from the US Gulf Coast or based on the US Gulf Coast. So capital costs will be different in other locations due to a lot of different reasons, right? You've got differences in labor costs, differences in weather, seismic activity, et cetera. And so as a result, we have what are termed either location factors or place factors. I've got an example here from Perry's Chemical Engineering Handbook, right? So a place like Italy, where it does not have very good regulations in place in terms of, right, labor can be very, very expensive. There, Southern Italy, there's still a lot of organized crime, drives up labor costs, cost of doing business, et cetera. Compared to a place like Japan, which even though it's an island, is a very, very law-abiding place, very well regulated, et cetera. Big difference in place factors, at least back in 1993. Again, place factors will change over time as well, but just gives you an example, right? You're basically talking Italy, the place factor is more than twice as much as Japan. And so if you're talking about it, the exact same type of facility in Italy versus Japan, same feedstock, same production, et cetera, that's going to be a big difference to your capital costs. And so location from a capital cost standpoint is also something that we always want to make sure we consider. So just to give you some examples right then, when we break out capital costs, and I'm not going to go into the specific acronyms on this because I want to make sure we have some time for questions, but you can get an idea, right? These are biomass systems versus natural gas systems as feedstock, different pathways, ultimately related to primarily gasification, right? Big differences between them. And so this is where we talk about using a scoping analysis, techno-economic analysis to ultimately show what, how these different pathways compare on a high level basis. Well, this is just showing differences in those capital costs, right? The total project investment. This is another one from a paper that a colleague I had at Iowa State wrote, right? Again, these were just 3 different ways producing cellulosic biofuels, in a couple different variations. And again, big differences in those total capital costs. And so again, techno-economic analysis, very good at presenting what these are going to look like once you put them side by side, similar assumptions, et cetera. Unit capital costs, on the other hand, right? So I said that unit capital costs and capital costs, especially under economies of scale, move differently. Well, these are the exact same pathways as are shown here, right? And ultimately what we're seeing here is that the total project investment per unit, gallons of gasoline equivalent, ultimately very different from the total capital cost on an absolute basis. And so that's again why, especially with differences in capital cost scale, we ultimately look at these very differently. There's a lot of variation between them that we want to try to account for. All right, so what drives those capital cost differences then? Well, some of it's practical, your choice of pathway. If we use the solar example, solar PV versus concentrated solar power. Solar PV, very distributed. Concentrated solar power, as the name suggests, just the opposite of that. Location, right? Building in upstate New York versus New York City versus India, big differences, in all those different criteria, all those different variables. What your capacity is ultimately going to be, right? You're talking very large, you're talking very small, and your energy output, right? The more energy output you get, the more valuable that is ultimately going to be. Whereas the more energy input that goes in, the less valuable it's going to be in the sense that your operating costs are going to be a lot higher. So this is where conversion efficiency becomes very important. You also have methodological differences. Choice of equipment, right? So what's your install factor that you're ultimately going to use? Laying is going to get a different result in hand than your Peters and Timmerhouse factors. Choice of your cost basis here. This is a very simple one, but you always want to show what your cost basis here is. Because I find some papers, they don't show the cost basis here, and you ask the authors and they say, oh, it's 2007. Well, 2007 cost basis in 2020 or 2022 now, right? That's going to be a big difference as well. And so those are the types of things you always want to account for. Choice of location factor, right? As opposed to your choice of location. So this is not saying site specific, but ultimately even something as broad as which country are you building in? Are you going to be talking about individual cities, states, et cetera, right? There's going to be a lot of different variables that you ultimately want to use. Got a question that just came in from Rick. So which TEA methodology do I use? I typically use the Peters and Timmerhouse factors. Main reason for that is, especially when I was doing lots of TEA, I was ultimately either building upon work that the national labs had done or was comparing it with work that they had done, because the national labs, right, especially when we think about NREL, PNNL, they've done some of the most widely cited techno-economic analyses of, really the pathways that we think about when it comes to the bioeconomy. And so building upon those, working with those, using them for comparative analyses, it made a lot of sense to use the Peterson-Timmerhaus factors. So that's ultimately what I've used, and then building in cost basis here, location factor, variables like that. All right, so see, we just have a couple of minutes left, and I know that there's already some questions coming in. So let me switch over here and just open it up for questions. Let me see. I see we got a couple others. Okay. Sal says, in the mass bio TEA analysis, where are areas that you think have the most potential to reduce the costs? Location of plant, improve technology, etc. This is a great question, because ultimately this is going to really depend on your technology. One of the reasons that we do TEA that I didn't mention earlier is ultimately to help identify areas that you can reduce costs, right? To find out, this is where we start thinking about sensitivity analyses, things like that. Can you ultimately figure out, right, is an improvement to your process yield going to have the biggest impact? Is a difference in location going to have the biggest impact? And so, you can't really say it for TEA, even in the context of mass bio generally, because there's going to be so many different variables that go into it. But this is ultimately one of the things that we would use TEA to do, is to identify those areas that do have the most potential to reduce cost. Karen says, we do not use TEA, or I mentioned, we do not use TEA to replace the site-specific cost estimation. However, TEA is a financial analysis that is considered particularities of the project, not only average data available. So you can get more detailed with TEA than just your basic high-level TEA. And so this is where, right, as you know, site-specific, what your shipping cost, etc. And so how has the wide range of plus or minus 30% uncertainty impacted feasibility of bioproduct plants? Well, this is ultimately one of the reasons that we have not seen the, really the bioeconomy grow as rapidly as probably was expected 15 years ago, is because that plus or minus 30% range, that is not enough for banks. This is not enough for financial institutions that are ultimately going to be providing the loans. And so, needing to do more specific analyses has been a very, very important part of this. It's gotten to the point, right? We've heard all about the DOE and USDA loan guarantee programs, and ultimately how they did not do, that we did not see as many projects funded under these as we expected. But you talk to the project developers, and what they would tell you is you had to put so much information into those. There was so much data that was required for these, that it was too much, too time consuming. They weren't willing to put in that much time and effort. So, that wide range of uncertainty, we have to narrow that down. And this is where you get sensitivity analyses are very useful. More importantly, uncertainty analyses become very, very useful to try to narrow down that range of uncertainty. But at the, the high level TEA, that plus or minus 30% range of uncertainty, that has certainly made it more difficult, right? You're not going to get a project financed if you have plus or minus 30% range of uncertainty at the end of the day. So this is why I say it's good for that initial high level scoping analysis, and you can make these, reduce the uncertainty via the criteria that Karen's comment notes. But it's never going to get to that point, right? You're going to have to ultimately do a more site-specific assessment in terms of getting financing. Looks like we have about one more minute. If there's any other last questions.
Dr. Brown, I have a question here. You presented TEA as something for kind of a factor, analyzing a factory that's processing biomass. Do you see TEA as having potential for analyzing other aspects of the broader regional biomass and bioproducts system?
Yeah, so ultimately we talk about, okay, that centralized facility, the processing facility. Well, if you want to know what the what that facility can pay for feedstock, that's good, right? This is, if you want to know, right, it all kind of links together, because if you want to convince farmers or landowners to grow a particular crop or a new type of biomass system, they're going to ask you, well, what's the financial return to me? And you can't really say that unless you know how much a processing facility or factory is going to be able to afford to pay for the feedstock. And so this is where TEA becomes very important, because you can figure out, okay, this is the minimum, something that we use in TEA is called the minimum fuel selling price, right? Which is basically the minimum production cost for that particular facility. Well, that in turn is going to tell you what the maximum feedstock prices that the facility can afford to pay. And so all links together then, because once you know what that maximum feedstock price is, you can do a separate TEA of, say, a biomass production system. It's not just for the conversion facilities. And you can find out, okay, we can actually produce it for less than what that maximum feedstock cost is going to be. And so it does tie together in that regard to figure out for the entire supply chain, is that going to be feasible to do? Any other questions? Okay, well, I
Terrific.
appreciate
Yeah.
Sorry, go
Thanks
ahead.
so much. I really appreciate you taking the time to share with us. It's a very interesting topic. I assume that if people have follow-up questions, they can contact you maybe by email, if that'll be okay.
Yeah, certainly. Happy to. Yeah, email's probably easiest.
Okay. All right. Terrific. Well, thank you very much, Dr. Brown. Really appreciate it. And
Certainly.
look forward to seeing everyone at our final Mass Bio seminar of the semester 2 weeks from today. Thank you, everyone.
Thank you.